Buenas tardes a todos y todas. Muchas gracias por su participación nuevamente en nuestra serie de webinars, programada esta vez para el mes de julio. Estos seminarios son desarrollados mensualmente en cooperación con 3 universidades nacionales del Perú. Tenemos a la Universidad Nacional Emilio Valdizán de Huánuco, la Universidad Nacional San Antonio Abad del Cusco y también la Universidad Nacional de la Amazonía de Iquitos. En esta oportunidad tenemos la presentación del Dr. Xiaofeng Liu, profesor del Departamento de Ingeniería Civil y Ambiental de la Universidad Estatal de Pensilvania, o Penn State University, quien nos brindará la ponencia titulada Building Computer Models Like Legos, Dynamics and Prediction of Coupled Fluid-Object-Sediment Systems. Esta presentación brindará algunos de los avances que desarrolla su grupo de investigación para caracterizar y predecir la dinámica y evolución de los sistemas acoplados fluido, objeto y sedimentos, y cómo se aborda la resolución de las ecuaciones diferenciales que rigen para todos los procesos físicos relevantes, como flujo turbulento, transporte de sedimentos, comportamiento del material granular y movimiento de objetos, en un dominio que cambia dinámicamente. Como mencioné, el Dr. Liu es profesor de la Universidad Penn State University, obtuvo su licenciatura en Ingeniería Hidráulica de la Universidad de Tsinghua y una maestría en Ciencias Ambientales de la Universidad de Pekín, en China. Además, obtuvo su doctorado en Ingeniería Civil de la Universidad de Illinois en Urbana-Champaign y una segunda maestría en Matemáticas Aplicadas en el 2008. Entre sus líneas de investigación tenemos la mecánica de fluidos computacional, CFD, el transporte de sedimentos, la mecánica de fluidos ambientales. Su grupo de investigación se especializa en el desarrollo y uso de modelos computacionales para la resolución de problemas de ingeniería ambiental y recursos hídricos. Muchas de sus investigaciones han sido financiadas por NSF y el gobierno americano, además de la industria. Les recordamos que este evento está siendo transmitido tanto por vía Zoom y YouTube. Posteriormente, la grabación quedará disponible para todos en nuestro canal de YouTube. Tenemos participantes que conectados vía Zoom pueden acceder a la traducción en simultáneo, hasta con acceder al botón inferior debajo de interpretación para cambiar de idioma. Y bueno, cualquier consulta que surja durante la ponencia, por favor, pueden hacerla a través de los comentarios vía Facebook o también en la sección de Q&A en el programa Zoom. Many thanks, Dr. Liu, for giving us your keynote lecture. It's a pleasure to have you here, so I'm pretty sure we will learn a lot today. I know everybody's waiting for you, so please, you can start your presentation now. Thank you.
Oh, thank you, Tanya, for the kind introduction, and also thank you again for invite me, and for those of you tuning in today, I welcome you to my talk. So as Tanya has introduced, I want to talk about today is some of the work we have been doing in my group at Penn State University, mainly on the computer modeling of flow, object, and sediment systems. So this work has been going on for a couple of years and has supported at least 2 PhD students and 1 postdoc. So the work is mainly funded by a program is called a SERDP, Strategic Environmental Research and Development Program, and also partially funded by U.S. Bureau of Reclamation. As you can see, there will be some examples I'm going to show today for the application side. So what are the motivation of this work? Objects or structures, hydraulic structures, for example, are everywhere in rivers and oceans, right? For example, in rivers and in oceans, you have gravel and boulders, right? Kind of a sediment being transported in these systems. And then you have woody debris, right? You can treat that these trees, branches, or these woody debris have some kind of a object, right? It's transported in river and streams, and occasionally they also interact with the sediment bed. Hydraulic structures like bridges, covered dams, right? So these structures that we built in river and streams, right? Definitely they have an impact on the system, and then they are part of the system too, right? So we are interested as an engineer, we're interested in the stability, right, longevity of these structures, and other examples of objects, right, and structures include pipelines, right, to transport oil and gas, right, and communication cables, right, like the internet that we enjoying today, right, is backed by thousands of miles of communication cables, right, under the ocean. And since this project is mainly funded by the startup program, right, so one of the mission is to mitigate the safety hazards induced by what they call the unexploded ordnance, UXOs, in the rivers, in lakes, and the oceans, right? So I'm going to show some examples later on, so you know what is that about. But anyway, those are the examples of objects, right, that we can think of that exist in the system of flow, right, in river flow, and coastal ocean flows, and the sediment bed, right? So as you can see on the right, there's this picture of a kind of a cartoon to show you, a kind of a simplified view of the whole system. So we have the air and water where we have interface, what we call the free surface, right? And that's what you see in the river, right? The surface of the river. And underneath that, there's another interface between water and the sediment, right? Which is the bed we're interested in. And of course, if you add an object or a structure, right, this thing is going to be more complicated. So it is of great interest to understand the dynamics and the evolution of the system. If you see this big picture on the right, as a dynamic system, because everything changes with time, right? And we are interested in how this change is going to happen and how it's going to the system going to evolve in time. Because as an engineer or as a scientist, right, you're interested in for example, in the future or back in the time, right, in geology, how things are going to look like. And if these objects or structures are mobile, right, if you put something into the river, it could be transported. So we're interested in the transport and also the fate of these objects, right? So if they can be moved by the flowing water. So to give you more kind of a specific examples on the application of these kind of a coupled flow object and sediment system. So I'm going to show you some slides, right, to show you both from the scientific point of view and also engineering application point of view, what is the usage, right? So why we are interested to study this. So first of all, I know many of you guys are working or expert in river dynamics, right? So the gravel and boulders or even any sediment particles, right? They're transported in rivers. So in this case, you're interested in the mobility, right? Transport of these gravel or boulder particles. Right? So why they move? Well, they move because of the flow, right? So when these particles move, as you can imagine, they interact, right? They interact with the flow itself, change the turbulence, change the flow structure, right? Itself, it's very complicated process. In addition, when these gravel and boulders move, right, they interact with the bed too, right? So if you know a little bit about sediment transport, one of the mode of sediment transport is called a saltation, right? So they just jump or hop, right, for a short distance and they go back to the bed. Because the transport of these particles, right, over time, the bed could change, right? You can have scour erosion, so again, right, this whole system, they evolve, it changes status from time to time, right? Especially during floods. So from the perspective of engineering application, right, one prominent example is bridge foundation scour, right? So if you build a bridge, right, for roads and for whatever transportation purpose, right, when these roads going across the streams, rivers, right, they have to build something, right, like a bridge, right, to support the abstract structure. So this foundation, right, is built into sediment, right? So this foundation or the whole bridge structure is the object, right, that we people place them into a stream, into the river. So, so in this example, right, this is a extensively studied topic, right? So people now understand how does the flow field or the structure look like, right? When the flow come in and meet with this structure, and how the flow going to go on the side of the structure, right? And in front of that, you can plunging down and create this what we call a horseshoe vortex, right? Which is the primary cause of sediment transport around these kind of structures, right? And of course, that's the cause of breach foundation scout, right? So the next one, next example is in river restoration, right? So this is an example that we have a project still ongoing to look at what we call large woody debris, right, or engineered log jams, right? The wood, right? For example, these trees, this wooded material, they are everywhere in natural streams, right? In nature. So they're part of the nature, or part of the system, right? So, and but in the past a couple of decades, people have done a lot of modifications to a lot of rivers and streams, right? So many years ago, we think that the primary function of river and streams is to transport floods, right? So to make it more efficient. Well, how do you make it more efficient? Well, reduce the flow resistance. Well, how do you reduce the flow resistance? Well, clear it up, right? Make it clean and nice, right? And to make it better, just pave it with concrete. But now gradually realize that the river is not only function as a conduit for flood flow, but also has ecology, right? Environmental values. For example, these are habitats for fish, right? So we're trying to restore many places in the United States and all over the globe. People are trying to restore the functionalities, the multiple functionalities of the rivers. One of the things we do here is to introduce larger wood. Instead of clearing them out, now we reintroduce wood into the channels. But there are still some questions about how do we do that, right? Do we understand how nature works, right? So a lot of unknowns, but in general, to reintroduce wood structure, like you see on the two pictures on the left, right? So basically what we do in the practice right now is just go and get some trees, right? And then stack them together, right? And then somehow place them, or either with a foundation or with the anchor, right? Sometimes just place them. But whether they can function well, right? For example, how does the flow dynamics going to look like around these structures, right? How does the sediment transport going to look like, right, around these structures, and whether fish are going to like it or not, right? So these are open questions, right? Again, this is one example of a flow, structure, and sediment system, right? So another example is in coastal structures, right? So in coastal areas, we have hurricanes, we have typhoon, right? And then we have infrastructures, we have houses, right? We have communities living in these areas. And if you put these infrastructures there, definitely is flow, object or structure, and sediment system, right? Because these foundations they're built into the sediment, right? If you have hurricane, if you have typhoon, right, it might cause a lot of damage, right, if these structures, the foundations are not designed properly. So as you can see on the bottom, right, there's some post-disaster survey. I think those are in Florida somewhere. After one of the hurricanes happened recently, as you can see, right, it caused a lot of damage, right? So as you can imagine, during the hurricane season, this is a big couple system, right, among flow, right, the coastal flow and waves, and the structure, right, and the foundation sediment, right? So like I said before, right, underwater pipelines and the communication cables, right, they're pretty important for our daily life, right, our modern life. So These scour around these pipelines and communication cables, right, also have been studied extensively in the past several decades. But still, it's an example in this general category of a flow, structure, and sediment, because these pipelines and communication cables, they're placed, right? They're placed on the top of the ocean bed, right? Sometimes they just place there. Sometimes they have some kind of a backfill or dig a little trench, right? And then, but overall, it's a coupled system. We're interested in how this flow and sediment transport dynamics is going to look like, right? Whether these pipelines going to fail or not, right? Whether these cables are going to break or not, right? So now go back to the underwater unexploded ordnance problem, right? Which is the main purpose of the project that we're doing right now, is that due to historical reasons, right? Especially after World War I, World War II, and the numerous other wars, and after war, there's a surplus of these munitions and bombs, right? They, at that time, people, don't know how to deal with them. Well, at that time, one obvious solution is just dump them into the ocean, right? Because if you dump at that time, they're thinking was if you dump far away off the shore, they will disappear, right? Well, believe it or not, after several decades, some of these things are being transported onto shore, and as you can see on the picture on the left, right? So some of these things being washed up to the shoreline, and sometimes kill people, right? And plus, it's an environmental hazards to to the environment quality. So one of the things they're interested in is the dynamics of these objects, right? So as you can imagine, these objects are similar to gravels and boulders, right? And under the hydrodynamic forcing of wave and currents, right? And they can be moved around, okay? So now go back to the to more general framework of these coupled system. I want to show here is a flume experiment video. This experiment was performed in University of Illinois more than 10 years ago. And what you see here is that initially there was a cylinder. It's made of steel. It's pretty heavy, placed on the bottom of sediment. Right? And then what you see is that they have this kind of oscillatory flow, the flow going back and forth, right? So as you see, these and with time, this object kind of moves and sinks down into sediment, right? So we are very interested, how this how this is going to sink, right? Why it moves this way? This is only one scenario that we can simulate in the flume. What people have observed in the field is that under certain conditions, for example, on a certain like large wave or large storm event, not only this thing can sink, but also sometimes it being scooped up, right? It kind of float up and then being transported to somewhere else. If you look at the whole process, right? It seems that this is an example of the flow, object, right, and sediment bed coupled system. There are a couple of key physical processes that govern the evolution of the dynamic system. Of course, first one is turbulent flow, right? If there's no flow, if the water doesn't move, or nothing moves, because flow is the driving force for everything here. And then we have sediment transport, right? We have a scour erosion around this object, right? So because of you have undermining or scour erosion around this base of this object, right? So it can fail, and sometimes it kind of rock back and forth, right, and find its new position each time. And also there is a large bed deformation, right? So you can have bed forms devolve and ripples, right? All these things gonna affect whether this thing gonna sink or float or even be moved away. And of course, right, this object has a 60 degree of freedom, a rigid body motion, right? It can rotate and can translate in 3 directions, right? So that's why you've got a 6 degree of freedom motion. We could also have what we call liquefaction effect, right? Because this sediment is not the concrete, right? It's a porous media. So if you have pressure, non-uniform pressure acting on the surface of the bed, right? So basically you have, pressure going back and forth, right? So the water inside the porous media, inside the bed, right, could build up its pressure. And when the build up pressure is high enough, right, it create this what we call liquefaction. So what it looks like is that certain part of the bed, right, behave like a liquid, right? It loses its supporting capacity for anything above that, right? So that's why sometimes we say the main cause of it could be the main cause of this motion of this object, right, sinking down into the bed is caused by liquefaction. So there are some control parameters, right? As you study any system, right, you look at what is the control, what's controlling here. Of course, the object density and shape, right? They are very important for the motion, right? For the hydrodynamic forcing and interactions, right, among different components. Flow intensity, right? So the larger the storm, right? The larger the flood, right? Of course, the larger damage, the larger the forcing. And sediment property, right? When you have a very fine sand versus a gravel bed, right? The whole thing will be different. And they're in an object shape, right? So if you have a cylinder, you have a sphere, right? All these things are gonna be different. So with those things in mind, right? How do we come up with a computer model to describe these processes, right? As you cannot see, and from my description, this is a very complicated process. It involves multiple phases, right? Multiple things and multiple physics, right? So, if you have some familiarity about computer models, right? Well, computer model is nothing but a computer code solve the governing equations, right? So what are the governing equations? The governing equations come from your understanding or our understanding of the physics processes, right? So what are the physical processes? Well, I already described a little bit in the previous slide. Well, mathematically, if you want to write down these physical processes, right, you have to write into governing equations. Now, I'm not going to show or go too much of details into what are the governing equations we use in these models. Well, essentially, it's nothing but like a conservation of mass, right? And then Newton's second law, or we call the momentum equation, right? And some other physical laws, such as well, under certain condition, how much of sediment going to be moved, right? Sediment transport rate law, things like that nature, right? So don't be scared about these complicated computer models, right? But inside, right, what's implemented is nothing but those fundamental physical laws. So as you can see, all these processes, right? There are more than 5, 6, or 7 physical processes, right? They're happening at the same time. Those are the building blocks, right? They're building blocks for us to come up with a more complicated model to describe these complicated phenomena, right? So that's why I'm saying this was building these computer models like a Lego, right? Each piece of the Lego is like one part of the model. Right? Let's say this piece is for, let's say, for flow, and that piece is for the sediment, right? And another piece is for the for this object itself. Now you have to stack and put them together in the right way, right? So they can work together and communicate with each other, right? As the time evolves, and then this is going to make a prediction on, well, I know what it looked like right now. What happens after 1 second, right? Or what happens after 1 hour, 1 week, right? And then you evolve the system in time, right? So, all right. So from the perspective of building these models, there are basically two communities working on, I would say the same thing, right? So I'm going to show you why I say that. One is from the hydraulics perspective. I guess most of the people listening to this talk now may be from this hydraulics research community, right? So traditionally, we only look at, well, we have the river flow, right? The flow in channels, and then we have the sediment bed, right? And then we have this object here. We, you know, from hydraulics perspective, we don't spend too much time to think about what happens underneath the bed surface, right? Which is the porous media or the soil. Right? So most of our hydraulics research focus on, well, if I can come up with a decent model to describe the flow field, right? The flow structures around these objects, right? And if I also can understand or know how to quantify the sediment transport rate, right, as a function of the flow, and then, you know, we can predict the scale erosion of this object. Right? So this is from the perspective of hydraulics. As I said, there's another community. They also heavily involved in the research of this kind of a problem, right? This is from the geotechnical perspective. So from their perspective, they are more interested in the behavior of the soils, right? We call it sediment, they call it soil, but essentially the same thing. So as you can see here, they are interested, okay, if I put something like build a foundation or put something on top of the soil, how does the soil going to behave, right? You're going to have some kind of a settlement, right? Or you have some kind of failure, you know? So they are interested in the things like a foundation design, the stability of a slope, you know, things like that, right? But really, we should combine these two perspectives together, you know, to have a holistic view of what's going on, right? So if you only look at what happens above the bed, you know, and missing the information underneath the bed, right? I think we are missing a big part of the dynamics. And from the other side, in a geotechnical group, right, people, they are more interested in the, well, how is the granular material going to behave? How is the soil is going to deform? If they don't understand what happens in the channel, right, like you know, the flow around these objects and above the bed, right, and you know, the pressure acting on top of the bed, right, so they have what we call it the pumping effect, right, in and out of the bed. They also miss a lot of physics, right? So we should combine these two perspectives together to come up with a holistic view, so we can have a better understanding of the physics in this couple of systems of the flow, right, the sediment, and the object in between. So what we did in my group is that we come up some kind of we are going into that direction. We're not there yet, but we're going that direction. So what I'm going to present to you quickly here is that some of the models we developed for each of these components, and hopefully we can have some kind of a coupling, right, between different components inside this couple system. So the first one is the traditional hydraulics perspective, right? So, well, we look at the flow domain first, right? So we solve the wave and current, right, in this channel, right, in this coastal area, and then by solving the governing equations, right? So the governing equation again is nothing but the conservation of mass for fluid, right, and conservation of momentum for a fluid, right? Newton's second law, nothing more than that. In addition, of course, you have to have some kind of a way to describe the turbulence, right? Now, in my group, we use the open source platform, OpenFOAM a lot, right? So we have been using that for a long time. So we have experience to develop our own model using this open source platform. And OpenFOAM, if you know about that, you know this is open source code, right? You use the finite volume method, right? And then you have to come up with unstructured mesh of your domain, and then you set up initial condition, boundary condition, and you can run it. And then what the code does is to solve your governing equations, right? So anyway, I'm not going to go to too much of details here. So essentially, we're using CFD, computational fluid dynamics, to to get to the flow information. And then, of course, for sediment transport part, we use sediment transport model for the scour erosion. For the second half of the domain, which is the porous media domain, right? We have another component, which is for the granular material dynamics. So this is more from the perspective of the geotechnical community, right? So in this part, we use another approach, which is called a smooth particle hydrodynamics, right? SPH. Now this is in contrast. This is a meshless method. I only use particles to discretize and solve the governing equations, right? So and of course for the object itself, we use a 6 degree of freedom rigid body dynamics model to describe the translation and rotation of this object, right? So I'm gonna go through each of these components, right, and tell you briefly what are they, and then I'm gonna show you some example applications. So CFD, right, computational fluid dynamics. Sometimes people call it colorful fluid dynamics, right, because most of the CFD results are showing in colorful pictures and animations. Essentially, like I said before, there's nothing fancy. Right, it just use some kind of method to solve the governing equations. Well, these governing equations usually in the form of differential equations, right? Well, these differential equations are nothing but our understanding, mathematical description of the physical laws, right? And I'm not going to go to the details of how do we discretize these governing equations, right? And how do you generate the mesh? Eventually, right, what do you have? What these CFD packages are going to give you, and after it solves the problem, is that it gives you the solution at the, for example, at the center of each of the control volumes, right, or cells you have in your domain, right? The cells are that are part of this, this mesh that you have to create for your simulation domain. Okay, so like I said, for the flow domain part, we're using CFD and sediment transport. Right, so hydrodynamics, right, the governing equation have a special name. It's got a number of those equations, right, and then you add the turbulence modeling into that. And for the morphodynamics, right, so we simulate or calculate the sediment transport rate, right? Sediment transport typically can be classified into two kind of modes. One is a suspend load, the other is wet load, right? And then when you have these the transport rate for each of the transport modes, right, you can use the conservation mass for the sediment in the bed, right, which we call Exxon equation. If you solve that, it's going to give you the updated elevation of the bed at every time, right? And then you can march in time and to see evolution of the bed, right? So nothing fancier, nothing fancier than that, right? But there's one particular thing I want to point out is that over the years, we adopted a method called immersive boundary method. Right? So I'm going to show you what is that, right? Traditionally, or many years ago, me included, we use a method. It's called a mesh deformation method. Right? So the idea is that is the following. So initially, I have the bed. Right? If you look at my cursor, initially I have the bed here, and with time, the bed kind of be eroded right into a new position. Mesh deformation method says, okay, yeah, well, if you move, right, these grid points are going to move accordingly. Now, this method is very simple. Basically, you're deforming or stretching the mesh points. But the limitation of this is that it can only deal with very simple geometry, like something like a vertical cylinder. If you read the papers and literature, many publications, right, in this area, yeah, they can simulate the scale, but if you look at the application example, yeah, it's scale around a vertical cylinder, right? One of the reasons that they can only do this is because the limitation of the mesh deformation method, right? For example, they cannot simulate a very simple bridge pier, right? So we have a bridge pier and they have a cap or with a subgroup of sub piers, piles. And how do you do that, right? It's very difficult to do mesh deformation. So to give you some example of that, right? So this is an example showing if you use mesh deformation, this is what's going to happen, right? So you have vertical pile, and then you have sediment transport around this pile, right? Due to the current erosion. And if you look at the inside the scour hole, right? As you can see, deep in the scour hole, the mesh is being stretched, right? Being stretched. But in the deposition part downstream, right, the mesh is being squeezed. Right? As you can imagine, if your scour hole is very big, the deposition pile is very tall. Now it could make the mesh quality deteriorate or even make the simulation diverge. Okay, so that's the reason that we use a different approach. It's called immersed boundary method. Right. So in this immersed boundary method, the background mesh, the mesh itself does not change. What's changing is the interface. Right. This interface, for example, here I noted as the blue line. Now this interface is free to move around, right? But its effect, let's say this is the wall, the bed, sediment bed, it moves around with time. Now its effect to the flow, right, is being treated as use this immersed boundary method, right? So I'm not going to tell you the details about the what is immersed boundary method and how do we do that, right? In fact, we have a paper on this. We improved the immersed boundary method, which we didn't invent, right? It's invented by people in biofluids, right, to simulate things like a heart, right, pump effect. So if you're interested, you can have a look at this paper. So next, I'm going to show you some examples using the immersed boundary method that we developed and that we improved, right? One of the important improvement of our immersed boundary method is to produce a smooth wall shear stress, right? Because wall shear stress is the driving force for sediment transport. If you don't have a smooth wall shear stress, right, the sediment transport is going to be all messed up, right? The result is not going to be good. But anyway, what I'm showing here is some hypothetical cases where I have a sediment bed initially is flat, and then I put the an object, in this case is ammunition, and also we prescribe some kind of a settling velocity, right? It settles pretty slowly until it kind of stops, right? So in this case, as you can see, the incoming flow is 0.5 meter per second. The sediment is 500 micron. It's typical sand. As you can see here, is that our model can simulate the evolution of the bed, right? The scour and erosion in the vicinity of this object, right? So, so next I'm going to show you is that now with this model, you can explore the effect of different parameters, right? For example, what about the angle of angle of this object, right? The previous case we have perpendicular. The object is perpendicular to this incoming flow. The next one I'm showing here, it has a 45-degree. Right? If you compare previous animation with this animation, you find out this angle of attack has a dramatic impact on the scour and the deposition pattern around around this object, right? And of course, that pattern gonna impact the mobility, right? Mobility or stability of this object, So I think the next one is another example I'm showing here is that the incoming velocity, remember, is 0.8 meter per second. Now, as you can see, initially the bed is flat, as you can see here, and then there's kind of a sediment wave coming in from the inlet, right? You can imagine, think of this as some kind of a bed form coming. Now, when the bed form comes and meet the object, right? it seems that our model can simulate the burial of these objects, right, under the peak of this bed form, right? And you can imagine if you want to use the traditional method of using mesh deformation method I showed in previous slides, right? It's going to be very, very difficult to do, right? So now all these examples, right? They look fancy, right? Looks like about right. But in order to really calibrate and validate our model, to gain more confidence into the result, right? What we did is we compare our result with some flume experiment we performed in our lab. So what we did is we segregate the part of the physical processes out of the problem. So what we did is we put these objects. We have actually two objects. One is the cylinder, right? So kind of a short cylinder. The other is the real ammunition. What we did is we put these two objects onto a cradle, so it's fixed. It does not move, right? So otherwise, it's going to be too complicated for this model to really capture everything. So you will see on the right, right? So how does the cradle going to look like? And then this thing is being buried inside the sediment, sand. And then we turn on the pump, and then we record the flow information, and then we measure the scour erosion around this object. So this is how does it look like, right? From the side, you can see here, and these red lines are the measured scour profile along this center of the slice. As you can see, with time, the scour erosion kind of propagate underneath, right? Because this thing is fixed on this cradle. So what happens is they initially, I think I can show you the animation here. Initially, hold on, let me change the pointer. So initially, the scour erosion happens at the two ends of this cylinder. And then the scour holes on both ends kind of expand. Eventually, they meet in the middle, right? And then everything underneath kind of be dug out, the sediment being dug out. There's forms a joint, big hole under this object, as you can see here. And then the sediment being excavated underneath this cylinder and then be deposited downstream. And this matches well with what we saw in the experiment. Right, so in the experiment, we measure the scour pattern at the end of experiment, right? On the left is the experiment, if you can see here. And then on the right is the numerical simulation, right? They're not exactly match, but as you can see here, at least the pattern and the magnitude, right? It's in agreement. So we also did the same thing for this ammunition object, as you can see here. Now the general trend of the scour erosion with time, it looks similar, right? So the scour erosion starts at two ends of this object, of the ammunition. However, the progression of this erosion or evolution of this scour hole is kind of different, right? It's kind of different than a cylinder case. So that raised the question about, in the past, people have used what they call a surrogate model, which means, well, instead of people have done other research that in the field and also in the flume. Well, instead of put a real like a shape object like a munition, they simplify this thing as a cylinder, right? So what we find out here through this modeling exercise is that the shape matters. As you can see here, the shape of this real munition has a kind of a tail, right? And then have a very thin or very small section, and then you have this head section which is larger in comparison to this uniform size of cylinder. So the hydrodynamics, right, the flow structure and sediment transport scenario are different, right? So you cannot exactly reproduce the process using a simplified cylinder, right? So that's one thing we find out. And of course, with the numerical model, you can extract more information. For example, at every time step, I can extract what is the lift force and drag force acting on this object, right? As you can see on the first figure on the bottom here is that they're different, right? And also I can extract the amount of a sediment scour anti-position separately, right? And then compare them. Again, there are difference, right? In fact, there are dramatic difference between a cylinder, a simple cylinder, and the real shape object, right? So the shape does make a difference here. So that's the part for the flow itself, right? For the flow domain, where we have the turbulent flow field, we have sediment transport. All this is traditional way to model the flow domain part. But what about the granular material part? Now, in this case, the granular material part, we have two phases. One is water, which is liquid, and then we have sediment, right? The sediment is saturated, so it's a saturated sediment. There are interactions between these two phases, right? As you can imagine, because porous media flow. So we, as I mentioned before, we use what we call the meshless SPH method, right? Using particles. Well, if you use meshless method, right, you don't need to generate the mesh for the simulation domain. Well, one advantage of doing that is that you don't need to worry about how this mesh is going to change, whether it's going to change or not, right? Do you need to use immerse binder method and things like that? So with the meshless method, since these are the particles, right? So there's no need to worry about mesh. And then you can simulate a very large deformation of the domain. We have a very arbitrary interaction of these objects with your sediment, right? So which I'm going to show next. So this work is done using the SPH code, which is also it's called a dual SPH physics, right? It's open source. So the basic idea, like I said, right? Again, I'm not going to go to the details of these methods, right? Basic idea is where you discretize your equations instead of using cells, right? You use particles, right? And then for each particle, they have to obey the things like conservation mass and the momentum equation, right? So that's it, right? So that governs how each of these particles move, and collectively they describe the behavior of the saturated sediment. Okay, and these saturated sediment, right? They're not the Newtonian fluid, right? So the difference between Newtonian and non-Newtonian, of course, right? Water is Newtonian, you know that, and the shear rate and the shear stress is linearly proportional. But for saturated sediment, they're not. They're not linearly proportional. So people have come up with different rheology models for saturated sediment, right? Again, we use one of the model that popular models that people have proposed. Right? Again, I'm not going to go to the details of these models, so you know that the sediment is not saturated sediment is not the Newtonian. Now, to put everything together, you have two phases, right? You have water and you have sediment, right? What about the object, right? Or if you have a structure? Well, this object, if they're movable, right? If it can be moved, we have to simulate the rigid body dynamics. So how do you solve the rigid body dynamics? Well, essentially you have to give the information on the forcing and turning moment on this object, right? Force in XYZ direction and the turning moment in XYZ direction too. And then you solve 6 governing equations, right? To solve the velocity in XYZ, rotation, angular velocity in XYZ, right? With these 6 variable information, you can update the position and orientation of this object, right? So that's it, right? Nothing fancy here. So I'm going to show you some examples. One is, if I have oscillatory flow, right? Remember the animation I showed at the beginning. So I have a box here. So let me make it laser point. So I have a box of sediment. Initially, I have this object that I placed on the top of the sediment, and on the top I have the fluid going back and forth. I have prescribed some kind of a driving force for the flow to going back and forth. So the animation shows that, as you can see, this object, right, it kind of moves around, carried around by the oscillatory flow, and also it interacted with the sediment, right? And with time, the majority part of this object is being buried into the sediment particles, right? So this is an example showing you that this model consider the dynamics, right? The coupling among the fluid flow, the object, and the sediment dynamics, right? So here's another example that initially we have this object, right, sitting on the dry sediment, right? And then we have a kind of a dam break type of a flow coming. When the flow hits the object, right, as you can see that the object has a fin, right? Part of the fin is anchored into the sediment, right? So because the anchoring effect, the fin or the tail of this object is kind of being fixed there, but not the case for the frontal face, right? For the other side. So that's why you see it kind of tilt a little bit, but and move a little bit, right? Under the impact of this dam break wave. In addition, I want to point out is that if you look at the top view on the bottom, is that I'm showing the elevation of the sediment. Right? So when the wave come in, right, it kind of carries and carries a part of the sediment, right, and moves sediment around this object. So you see the bed or elevation, right, the color of the elevation is not uniform anymore, right? So this model can capture these dynamics of sediment transport on this wave. So next, I want to show you is some application of this model we developed, right? So now you have this model, what is the use of that? So since it's a computer model, right, you can change the parameters and look at their relative importance. So one of the things that we are very interested in is what is the effect of the density of these objects, right? As you can imagine, if we have a very light object, right, it can easily be moved around, right? Or if we have a very heavy object, it's not as easy to be moved around, but it could sink down into the sediment, right? So I think what I have here is the one demonstration by a collaborator of at the Naval Research Lab. So what he had here is a box. So hold on. So initially, it is a box with sediment on the bottom, and you have water on top. And then he placed a sphere. Actually, I think two spheres. One is this black sphere, as you can see here, right at the bed. And there's, if you look carefully, there's also a kind of a ping pong ball type plastic sphere buried inside the bed. So now what he did is to shake the box. So with time you'll see that if he shake it, right, using this kind of a cyclic kind of a motion, right, something like a wave, right? So the heavier black ball kind of sink down into the sediment, right? And if you shake it even harder, what happens is that the light ball, it kind of show up, right? It kind of float up into vertically into the water, right? So this is a very simple setup, right? But it has a lot of interesting things happening here. It demonstrates the importance of the density. So our model, you can easily change the density of objects. So what I have here is I have a box, right? Like you showed in the video in the previous slide. I shake it, right? But here, initially, this ping pong ball is buried in sediment, and it has a specific gravity of 1 point, I think is 2, right? It's a 1.2, right? Slightly heavier than water, but it's lighter than sediment, right? So if you shake it, right, this object is kind of floating up, right? The next example is that I'm going to increase a little bit of the density of this the sphere, make a specific gravity to be 4, right? So I placed it, initially put it placed on the bed. So now if you shake it, as you can see, it moves around, but it doesn't sink into the sediment, right? Because of the interactions and because of the density such that it does not sink. Now, what if I even increase the density more, right, to make it specific gravity to be 7.8, right? So this is like a steel, right? Now, this object is much denser than water, right? Even denser than the sediment, right? So what happens is that initially it placed on the top, right? If you shake it, right, and with time it's going to sink down into the sediment, right? Because the sediment doesn't have the enough capacity to support it, right? So it kind of flows down. The last example I want to show before I conclude is that we work with the University of Delaware, our collaborator there, Professor Jack Polio. So what they did is they in their flume, they have a wave flume, and then they have a setup of kind of a dam break wave coming, and they have a sediment beach, right? So let me see here. So they have a sediment beach, if you see my cursor. And then what they did is they put a sphere or object on the surface of the beach, and then lift the gate. So, and then the dam break wave are going to come in and hit the beach slope, and then hit the object, right? So what they did is they use high-speed camera to look at the dynamics in the process, right? So and we simulate the same thing using the same setup using our model. The good thing about computer model is that you can, get way more information than in the experiment. Right? So here, when you lift the gate, the water kind of collapse, right? Create a wave and come in here along the surface of the slope, and then when the water hits the surface, the object, right? It kind of start to move it, right? Start to move it, and then accelerate that and push it forward and toward the end of the flume, and then run this again, and hopefully you can see this animation and get the idea what it look like. Now it hits the surface of that, and then it start to move, right? And again it's a momentum, and then being thrown to the end wall and hit the wall and then bounce back, right? So I'm going to run this one more time before I move to the next slide. Is that when you see that the wave come in, right? So hold on, let me stop that. Maybe we can stop here. Is that now? This is the hold on, go back. So I want to stop at the moment that the water hit the surface of the sphere. It seems that at the very beginning, you see, even when the water goes around this sphere, the sphere doesn't move. So in the sphere, it needs some time. It needs some time to react, right? Part of the reason is this sphere is half buried in sediment, right? So when you push the half buried sphere, the sediment still have some capacity, right, to support and resist that kind of motion. It takes some time for the flow, for the wave to impact and dislodge this object, right? And then once this thing is dislodged, right, it's much easier to be moved. So if you go further, at this moment, as you can see, it start to move, right? So it start to move, and then it gains momentum energy, right? And so speed up and then being slammed into the end wall. So like I said, with computer model, you can get more information. One of the information which is almost impossible to measure in experiment is the force acting on this object. Let's say, in rivers and channels, right, you have gravels, right? If you're interested in the transport of gravel and boulders, you're probably gonna look at, well, what are the forces acting on this object, on this gravel? And same thing here. If you want to look at the dynamics of this object, right, motion, then you definitely need to know, well, what are the force, right? Force at X, Y, Z directions, right, as a function of time. In experiment is hard to measure, right, because it's impossible to measure. But with computer model, you can extract that information. So what I'm plotting here is the force X in X, Y, and Z directions, right? So as a function of time, and you can look at the different time snapshot, right? For example, at the beginning, right, everything's in equilibrium. There's no force. The only force it has is the sphere, the object experiences gravity force, right? So in X, right, streamwise direction, span-wise Y direction, all the forces are zero, right? Only in the vertical Z direction you have force of gravity. So the interesting happens when you have initial contact, right? As you can see here, here. So let me see. Is here in initial contact you have a little blip of this force. The much larger force happens when you have more or less the whole thing is engulfed or be submerged by the impact wave, right? Which happens in this instance, right? You have this large force, which dislodge the object and start to move it. And then once this object moved and hit the end wall being bounced back, right? As you can see here, this black line shows a large magnitude of force, right? It's all simulated by this model. All right, so hopefully I convince you that if you build these models, you understand the physical process, right? You can come up with a decent model and then use these computer models that you can extract values or more information of interest, right? You can, with these models, you can make a play-by-play analysis, right? Make it possible. It's very hard to do experiment and even harder in the field. And you can test your hypothesis, right, on control parameters. For example, you already show the object, right? Its density is important. Its shape is important. Well, how important, right? And you can play around with these parameters and you can compare the results. And it provided quantities that's hard to obtain in the lab. For example, the force, right, on a moving object, right, under the force of hydrodynamic forcing. And it can provide parameterization for large-scale prediction models, right, such as the drag force, lifting force, all these forces. It can be plugged into large-scale models, right, for real-world applications. Now, all these cases I'm showing here are small scale, right, in the flume, right. There's no way for currently. There's no way for our detailed model that I showed today to be applied into tens of miles, right, kilometers long domain. So, but the value of our small scale model is that we can extract some information, some of the coefficient, which can be applied or plugged into large scale models for a real world application. So to summarize, right, hopefully these examples show you, to give you an idea that many of the things we're dealing with, right, in rivers and in the coastal areas can be simplified as or generalized as flow, object, or structure, sediment system, right? This is a very fundamental system and has a lot of applications. And the second message is that we need to have a holistic view of the system in order to advance this field, right? We should think out of the box of a hydraulic engineer or out of the box of a geotechnical engineer's perspective, right? We have to combine both together, and computer models are very useful for examining and for prediction. So with that, I want to conclude here, and then want to see if there's any questions. I will be glad to answer those.
Xiaofeng, thank you so much. I appreciate your presentation. I really enjoy.
Oh, thank you.
I see that you went with many applications after I initially started your work, and I really love it. So going from, I remember your deformation model, now the inverse boundary
Yeah.
method. Also, I have seen your work on that, but the application, the range of application that you are showing, it's I think it's fantastic. And so I have my own questions, but there are some questions here from the audience, and I'm going to pick some questions from the Zoom and from Facebook, so I'll let you know.
Okay.
Colin Ortals, he's asking, from this type of models, how difficult is or it will be to incorporate into a larger scale models? For example, in the coastal case to UXO, maybe that's
That's right. That's correct.
yes, coastal case to understand movement over the duration of a year. So that's I'm calling his interest in the coastal environment that he's studying in University of Florida. So go ahead, Shofen.
Okay. Oh, that's a very, very good question. So, and as I mentioned, this couple system, has a multiple physics, right, and have multiple scales, right, both spatially and time and temporally, right. So what my group has done in the past couple of years is that we build this small scale detailed model, right, to try to look at the detailed physics happening in the system. I would say it's going to be very difficult to directly apply our model to a large scale, like I said, tens of kilometers or hundreds of miles of a big domain, or apply it for a long-term prediction, right? At least, from my perspective, it's impossible to directly use our model. However, like I said, the information we extract from our small scale model can be used in these large scales models. I know our collaborators and other researchers funded by the program, they are developing things like a Delta 3D model, which can be applied to a large scale and long term. But they're begging us to tell them things like, well, what kind of a drag coefficient should I use? What kind of a lift coefficient should I use for different shapes, right, at different size? So that information is critical for them. And I can imagine if you double the lift coefficient or double the drag coefficient, right? Those key parameters gonna make the prediction way off, right? So what we are doing here is to kind of constrain the values of this coefficient. So I think that's the that's at least for now, that's the value of the small scale models. But anyway, that's a very good question.
Yes, and thank you, Shofen. Colin works in the field, so that's maybe
Yeah, I know.
on this scale. So I have another question from Cesar Espiritu. I'm going to rearrange a little bit the question. He's asking more. In Peru, we do have coastal rivers, Amazonian rivers. You have been in the Amazon a few years ago when we organized a conference there, but also we do have high gradient rivers, right? We have these mountain rivers with boulders, with not only sand, but maybe gravel material, cobble. So what he's asking more of what would be the effect of having these high gradient rivers and the simulations, or basically, can you simulate those environments using the same techniques that you have shown in your presentation, maybe?
Yeah, I think that's also a very unique, a very interesting topic in high grade and high slope channels. In these cases, I would imagine if you have a flood, right? Probably some of the traditional sediment transport series does not apply here. Traditionally we think, oh, the sediment transport rate is a function of the shear stress, right? Basically, you're peeling off like sediment particles, one layer at a time on the surface. But in reality, probably a multiple layer of sediment, right? They're moving at the same time. So this granular material behavior, right, probably also plays a very important role for sediment transport. So, our model could have the potential to combine both, right, the traditional like a shear stress turbulence kind of a theory with the granular material kind of a series, combine them together. So that's why I'm saying we should have a holistic view of what's happening above the bed, right? But also what happens under the bed, right? So I don't know. This is I think this is an exciting or a very interesting direction to consider. I know in the past that people have thought about that. For example, Professor Parker and his students look at the, let's say, the groundwater effect, like the seepage effect, right, on the mobility of sediment. So in a way, this is somehow combine the granular material behavior with the sediment transport. So, but that's a very good question. I think it's a very challenging problem too.
Yeah, we do have lots of examples here, from the 6,000, 7,000 meters above the sea level, all the way to the ocean, 100 kilometers. So that's, you have a lot of different reaches along the river that you have different sediment transports and different flow dynamics and so on. So very good, very good. So I have a question here from Juan Guamani. I'm going also to rearrange a little bit the question in terms of, here in Peru and South America, but let's focus on Peru. We have the El Niño, every several years. This that starts in the ocean, and then depends on where it starts. It's called, it has some numbers, 3 and 4. If it starts near the coastal part of Peru, it's 1 and 2. There is some regions in where these atmospheric processes are happening. And every time that happens that in Peru, we have a lot of flooding, rains, and we have a lot of erosion, deposition, and the main infrastructure like roads, bridges, and railroads, and most of the infrastructure is damaged. Okay, and what his question is going, okay, if you can couple your model, with maybe these ocean atmospheric models, with, I would believe what he's trying to say is also with the sediment transport models, and try to do some research. For example, I'm going to try to give you an idea there. What kind of Niño will produce the highest reworking on the sediment part in the continental, at least in Peru. I don't know if you have some thoughts on coupling your model to more ocean atmospheric models too.
Yeah. So I think this is possible. And again, with because this project is funded by a startup, we have multiple researchers in this, and Naval Research Lab, they have from what I heard is they have this operational model. So something like what you mentioned, Jorge, in the question, and they have this large scale atmospheric model at the driving force for driving force for these ocean or coastal model, large scale. So these are large scale models, and then, but again, they have to, if you look at the resolution, like grid cell could be like 1 mile by 1 mile, right? So anything smaller than 1 mile, you don't see it, right? The model cannot see it. So this is the place that these small scale models can be embedded inside, right? So this small scale model can extract the information from these large scale models, right? Say, how much sediment coming out, right? Coming in, how much going out, and the wave gauge, right? What is the time history of the wave coming and goes out? With that, probably you can, carve out a small patch, right? Let's say 1 mile by 1 mile. That's doable. You can look at, well, what's going to happen? Really, if you put something more interesting, if you have an infrastructure inside, right? Let's say a platform or an oil rig, right? Or a bridge, whatever things you have inside, what's going to happen? Because their model cannot do that.
Yeah, you're right. And using different models at different scales, and I believe the resolution is an issue, and maybe in few more years there will be increasing the resolution. So with increase of the computational capacity. So
yeah.
But you're right. I do have a question from Efraín and we, he's congratulating you for your presentation, but also he's asking, and also I will interpret his question is, sediment, like a particle moves in saltation and rolling down, and different type of mechanisms, right? Particularly if we think of as a particle, a small particle. And then the particles, when they are, they have collisions, they have different particle-to-particle interaction. Maybe the question is, are you modeling all of these different mechanisms on particle-to-particle interaction, or is a bulk, kind of a conceptual model?
Yeah, so I understand the question. So in our model, we actually don't track like each particle, are they gonna like do saltating or being swept by the turbulence or ejected from the bed. We actually don't model that. In fact, we treat the porous meters, the sediment bed, as a saturated kind of a non-Newtonian fluid. So that's the approach we take. Of course, this non-Newtonian fluid has, have parameters like the yield, the stress, right? And then you have these parameters to look at this non-Newtonian and how nonlinearity, shear thinning, this kind of behavior. So long answer short, to answer your question, we do not simulate each of this particle saltation.
Great. Yeah, that was quite clear. I think Efrain also, I think he was asking on that. Thanks, Xiaofeng. I do have a question from myself.
Okay.
You have modeled different shapes of objects, very complicated shapes, and also the last one on the Semen Beach, where you have this sphere, and you were showing the forces around the sphere, and that it takes some time to get mobilized. That's very, very interesting. I do have a question. Have you tried to install, because maybe you are doing some plume experiment, have you tried to install devices inside of the objects to measure the forces, the real forces on the object?
Yeah. Yes. So they do. As you know, I'm not an experimentalist, so that's why we need to work with experimentalists. So our collaborators, they have developed a very complicated and very sophisticated instrumentation on board. I think they call it IMU, like an inertial measurement unit or something like that. Right? So those things you can buy off the shelf. I heard, some kind of this little battery, and then you have these instruments like a accelerometer, things like that, pressure sensors. They do have that, so they can record the acceleration of motion and the rotation of these objects. So they can record that. But and of course from that they can back calculate what are the total force on that object. So yeah, with this very valuable information for us to calibrate our model. But yes, to answer your question, they do have a lot of that. I think Marcelo also, like Blake, when Blake was in Illinois, they developed something similar too.
Yeah, okay. No pressure, but Marcelo Garcia is on the audience here today. So.
Yeah.
No pressure.
No pressure, okay.
I do have another question from Magali Ayuke that you can read it also in the chat, but she's saying that, thank you for your presentation. When we would like to simulate particles using SPH approach, which are the main parameters to take into account? Taking account, maybe what are the main parameters to take into account that are maybe in the range of the particle diameter or something like that? I think that's the question.
I think the property of the saturated sediment, right, depends on the diameter of the particles, whether you have cohesive force or not. All these things are going to affect the behavior and the physical behavior of sediment. In our model, all these behavior are simplified as non-Newtonian behavior of the saturated sediment. So most of the parameters are in the non-Newtonian model, the rheology model, like the Euler stress, and the parameter, in other parameters in the power law for this rheology model. So those are the key parameters that we have to calibrate. Depends on different particles that you have. Other than that, I think and probably also important is the compressibility of the water, because the compressibility determines, or at least directly impacted the pressure of the water inside the sediment, the pore pressure. Right. So when the pressure changes, then you change the behavior of the sediment particle. So those are the key parameters I can think of, which we should calibrate, right?
Thank you, Chauffeur. And this will be the last question. You showed some experiments in a straight channel where you did a comparison with measurements and modeling on the bed elevation.
Mm-hmm.
And you were discussing that you captured the pattern, not exactly the bed surface. I was wondering, are those experiments, or were those experiments clean water experiments, or you have recirculated sediments in the experiments? And how did you account the boundary conditions in the modeling portion?
So in this case, we we specifically designed the experiment to be clear water scout, meaning that a sediment only moves in the surrounding areas of the sediment because of flow contraction. In other areas away from the object, sediment does not move. So clear water, for those of you not familiar with scout, basically we have clear water and live bed. Clear water scout typically has a larger scout depth than live bed. Typically, not always the case, but so that's why we designed the flow conditions such that it's a clear water scout. So we don't need to worry about the sediment incoming and outgoing. We would like to expand our experiment to include some kind of a live bed, and our model definitely can handle that, because you just specify in the incoming how much sediment, what is the sediment transport rate, and outgoing, right? And then you can even make a loop, right, to recirculate that too.
Thank you, Xiaofeng. And for I enjoy your talk and happy to see you. And I'll let Tanya to finish the webinar. And thank you, Xiaofeng. Thank you.
Thank you. Thank you.
Muchas gracias, Dr. Leo, por your time, por su tiempo, y muchas gracias a todos los que nos siguieron el streaming vía Facebook y a quienes se pudieron conectar vía Zoom. Les esperamos el próximo mes en el siguiente webinar mensual que está programado para este 25 de agosto. Muy pronto vamos a publicar mayor información. Va a ser otra vez un tema muy interesante con ponentes y expertos internacionales como el Dr. Liu. Gracias nuevamente a todos. Nos vemos.
Thank you.
Thank you so much.
Thank you. Yeah, by the way, if you guys want to need more information, you can go to my website. And most of our computer models are on GitHub, right? You can download and free to use.
Fantastic.
Thank you. Okay.
Bye, Xiaofeng.
Okay, bye. Bye.
Bye-bye.